Welcome to this MOOC on lasers. In the last lecture, we discussed about rate equations in a 3-level system, and today we will take it up further to the 4-level system. First, a very quick recap of the 3-level system. So, the scheme of amplification is shown here. That is the 3-level amplification scheme, where you consider 3 atomic energy levels of the system. So, the ground state, an excited state, upper excited state. A pump of energy h nu p, which raises atoms from the ground state to the second excited state, and from there they make rapid transitions to the level E2 with population N2 here, and then this is the level which is the metastable state, or which is the level that has a longer lifetime. Because the level has a long lifetime, atoms tend to accumulate here, and as qualitatively shown, at steady state the number of atoms N2 can be greater than number of atoms N1 if we pump it sufficiently hard. Because the transition T32 is a fast, usually non-radiative transition, the number of atoms at level 3 or N3 is much smaller, usually very small, because as soon as the atoms reach there, they go to level 2 by a fast non-radiative transition. So, the scheme illustrates, and we had also obtained an expression for the gain coefficient, and the expression for the saturated gain coefficient is here. Gamma of nu is equal to gamma 0 of nu. Gamma 0 of nu is the small signal gain coefficient. So, this is the small signal gain coefficient divided by 1 plus I nu by I s, where I nu is the intensity of the radiation which is being amplified, and I s is the saturation intensity. The expressions for I s are given here h nu divided by sigma of nu is the cross section, and tau s is the saturation time defined in this way. So, we have made this derivation and we have seen this. Now, since T32 is much larger than T1, so here T21, that is here, T32 is much larger than T21, this is fast, this is slow, T21 is slow, then we can simplify this further. Wp is of the order of T21, we have seen that at threshold Wp is equal to T21, and above threshold Wp may be slightly greater than T21, but it is of the same order as T21. So, Wp is of the same order as T21, but T32 is much greater than T21, and therefore, this Wp here 3 Wp here can be neglected in comparison to T32, and then T32 and this T32 cancels, and therefore, we have tau s is equal to is approximately equal to 2 by Wp plus T21. This clearly shows that as Wp increases, that is the pumping rate increases, tau s drops down and Is goes up, because in the expression for Is saturation intensity, tau s is in the denominator. So, similarly, for gamma 0 of nu is given by this expression, and as Wp increases, gamma 0 would also go up, and therefore, the variation of gain for different pumping rates would be as shown in this diagram here. So, this clearly shows that as the pumping rate increases, the small signal gain coefficient gamma 01, gamma 02, gamma 03 will be higher, and the corresponding saturation intensities are also higher. So, they are qualitatively schematically shown in this diagram how the gain curve changes with the pumping rate. So, for 3 different pumping rates, we have shown that the extent of population inversion will be different at different pumping rates, and therefore, you have different curves. Now, this extent of population inversion will be different can be easily recognized or can be easily identified if we take a simple example of with the analogy with a water bucket with a hole near its bottom. So, there is a water bucket here. So, this is the water bucket in which there is a small hole near the bottom. If you pour water into the bucket, water would go out from the hole, and when the rate at which water is poured into the bucket becomes equal to the rate at which water goes out of the bucket, we will have a steady state. For example, if we pump at a rate of WP1, that is a certain rate at which water is pumped into this bucket, then the level will build up to a certain level, the level will go up to a certain height, so that the pressure with which water goes out of this hole will be such that the quantity of water going out, rate at which water goes out, will be equal to the rate at which water is poured into the bucket. If we start pouring at a higher rate, then naturally the level has to go to a higher level now, higher height, so that water goes out with higher pressure, so that the rate at which water goes out increases. So, the point is, depending on the pumping rate, the water level will be different in the bucket. To reach steady state, that is the rate at which water goes out will be equal to the rate at which water comes in, then we have a steady level in the bucket. Same thing is true here. In the atomic system, if you pump harder, then the extent of population inversion will be different. The extent of population inversion can be compared with the level of water here, and therefore, the small signal gain coefficient will be different, and then the gain varies as per the expression for the saturated gain coefficient, and as we have discussed, as WP increases, IS also increases and gamma 0 of nu increases. All right, let us take example of the Ruby laser amplifier. We had mentioned that Ruby laser is a 3-level example of a 3-level system, and let me take the example and calculate what kind of pumping power is required to have lasing action in a Ruby laser. So, what is shown schematically is the Ruby laser. There is a Ruby rod. Ruby is a chromium doped alumina. The color, the pinkish red color of Ruby comes from the chromium doping, and typical doping concentration is 10 to the power of 19 per cc, and that is our N, that is the total number of atoms. So, these are the atoms which are participating in the interaction. It is the 3 level which we are discussing are the levels of the chromium ion. So, in the presence of a pump is generally a flash lamp. So, this could be a xenon flash lamp or krypton flash lamp, and the Ruby has pumping bands of blue and green around 400 nanometer or 400 nanometer or 550 nanometer. So, approximately 500 nanometer. So, that is why we have taken lambda p of the order of 500 nanometer. So, there are actually 2 absorption bands as we have seen earlier. So, the pump wavelength could be of this order, and near threshold WPT is equal to T21, and T21 we know because it is T21 is equal to 1 by lifetime. Lifetime is a measurable quantity. So, for Ruby it is typically 3 millisecond. So, we know the value of T21, which means we know the pumping rate, the threshold pumping rate WPT. So, let us see what kind of power is required to reach the threshold. So, N2 minus N1 equal to 0 is the threshold for amplification, that is just before N2 becomes greater than N1, and corresponding to that the pumping rate is WPT, is the threshold pumping rate. Assuming N3 is equal to 0, N3 is the upper level. Please see the mechanism that the atoms are excited to this level, but from here they rapidly go down here. So, that at any instant the number of atoms in this excited level, third excited level or the pump level N3 is approximately 0 or much smaller compared to these. And if N3 is 0, then N2 nearly equal to N1 equal to N by 2. N is the total number of atoms. At threshold N2 minus N1 is 0. Therefore, N1 must be nearly equal to N2 must be equal to N by 2. That is 50% of the atoms will be here and 50% of the atoms will be here, neglecting the presence of any atom at N3. Therefore, the pumping rate at threshold is given by WPT into N2. WPT into N2 gives us the number of atoms to be raised per unit time to achieve this kind of population inversion or just threshold when N2 is equal to N1. Therefore, the corresponding pumping power is given by multiplied by. So, this is the number. So, this is the number of atoms to be raised multiplied by the energy of photon raised per second. Therefore, energy per second will be the power. So, this is the power. So, this is the threshold pumping power. Threshold pumping rate multiplied by the photon energy of one photon gives you threshold pumping power. Maybe I have written somewhere, yeah, pumping power. So, we are now substituting WPT, we had shown that is equal to T21, which is equal to 1 by tau L. This is N by 2 is N2 multiplied by H, Planck's constant, into nu p, the pump wavelength, which is C by lambda. Lambda we have assumed that 500 nanometer, and therefore, this comes out to be 660 watts or of the order of 1 kilowatt. So, this matches with that of practical systems. Typically, ruby lasers require a threshold pumping power of the order of kilowatts. So, a very simple calculation tells us that okay, the numbers are all right, it is of the order of 1 kilowatt. We will see that if we go to a 4 level system, the pumping power required is much smaller. That is because we are creating population inversion between two excited levels. It is normally we know that the number of atoms in the ground state is much higher than those in the excited states. So, if you want to create population inversion between a ground state and an excited state, more than 50% of the atoms from the ground state have to be raised to the excited state, and therefore, the pumping power required is very high in a 3 level laser. So, in a 4 level laser, the population inversion is created between two excited states. Therefore, even if you have a number like 100 in one level and 90 in the lower level, you still have population inversion. That is the advantage of a 4 level system. So, the practical lasers such as helium neon lasers, Nd:YAG lasers are 4 level lasers, and we will take up the 4 level system. So, the 4 level system, the scheme is this, that this is the ground state from where atoms are raised to an excited state level 4. So, level 1, so this is level 1, 2, 3 and level 4. From there the atoms rapidly come down to level 3. So, this is level 3, and if the lifetime of level 3 is large, or if level 3 happens to be a metastable state, then atoms can get accumulated in this level here. So, we have large number of atoms here, the ground state, and then atoms are raised to the upper state here. from there they rapidly come down to this state, and if the level has a long lifetime, then atoms can accumulate here. When they come down to level 2, if T21 is a fast transition, that is whatever comes here immediately goes down to the ground state, that is if T21 is greater than or much greater than T32, then we will have net accumulation here and we will have population inversion between level 3 and level 2. So, this is level 2. So, this is what I mentioned, that you can create population inversion between two excited state by raising much smaller number of atoms. So, this is the scheme of amplification in a 4 level system. So, although there are transitions from 4.1, T4.1, T4.2 and T4.3, there are 3 transitions, which 3 types of transitions, spontaneous transitions that can take place from level 4. But in practice T4.3, in practical lasers, most of the practical lasers, T4.3 is much larger, the rate is much larger compared to T4.2 and T4.1. T4.2, T4.1 are of the order of 10 power 4, 10 power 5, 10 power 6, but T4.3 is much larger, of the order of 10 power 8 or 9. And therefore, in practice we can neglect T4.1 and T4.2, and therefore, if we neglect those, then our transition, our levels, our transitions will remain only this. So, we are raising atoms here, then they come down by this way only. The other 2 transitions T4.2 and T4.1 we can neglect, and then this comes down here and finally goes back. So, this is T21, this is T32, we are showing spontaneous transitions, and this is T4.3, and this is the pump WP. So, this is the 4 level scheme. It does not mean there are no other transitions, but other transitions can be neglected in view of the practical numbers. All right. So, now we straight away come to writing rate equations for such a 4 level. You can see here I have shown only T4.3 and T21, the other 2 namely T4.1 and T4.2 I have not shown at all, and therefore, we can write the rate equations at steady state. dN4, that is the population of level 4, dN4 by dt, rate of change of the population, is Wp into N1 minus N4. We can now directly write, because we know that Wp is the pumping rate here. So, it raises atoms from N1, and therefore, Wp into N1 is the number of atoms which are reaching here, Wp into N4 is the number of atoms which go out, and therefore, the net will be Wp into net addition will be Wp into N1 minus N4, plus atoms are also going down through spontaneous transitions here, which is T4.3 into N4. The negative sign says that N4 is decreasing because of this transition, and positive sign wherever we have says the number is increasing because of that transition. If we write dN3 by dt, then we have Wp of course. So, we have WL here. So, N3 will increase because of WL, N3 will increase because of this, N3 will decrease because of WL into N3 here, and N3 will decrease because of the spontaneous transitions. So, we have 2 positive terms and 2 negative terms. So, 1 positive term, 1 positive and 2 negative terms. So, similarly, we can write the rate equations for all the levels. Further, we also have n is equal to n1 plus n2, that is the total number n is equal to n1 plus n2 plus n3 plus n4. In practice, of course, most of the atoms are in the ground state. Therefore, at any time N1 is much greater than N2, N3, N4. In fact, even if you add all of these, this will also be much smaller compared to N1, and this can be written as N1 into the same way that we had done for the 3 level system. At steady state, as before, dN3 by dt, each one of them is equal to 0. So, recall the bucket, where at steady state, although water is getting poured into the bucket, water is going out of the hole, there is a steady state, and therefore, there is a certain level which is maintained in the bucket. Exactly like that, there is a certain number of atoms maintained at any given instant, at any time. Whereas, it is a dynamic equilibrium, photons are exciting atoms continuously to the upper state, from where they get de-excited, but there is a steady state which is maintained. All right. From equation 1, that is the first equation here. So, if we put dN4 by dt equal to 0, then this equal to this one, and this contains only N4 and N1. Therefore, we can get the expression for N4 by N1. So, that is what is written here, N4 by N1 is equal to Wp divided by Wp plus T43, and as indicated earlier, T43 is much faster because it is a high speed non-radiative transition, and therefore, we can write N4 by N1 is equal to Wp by T43. These are approximations which are practically correct approximations. So, instead of retaining large number of terms, we use these approximations right at the beginning, so that we get a small compact expression which is not very different from the rigorously correct expression. Similarly, from equation 4, now we look at equation 4, that is the fourth equation here. This also has only 2 terms. Therefore, if we put dN1 by dt equal to 0, we can get the ratio as shown here, Wp into this equal to this one, which means it is here written. We have substituted for N4 by N1 from here, Wp by T43, and we have an expression for N2 by N1 is equal to Wp into T43 minus Wp into this. As before, since T43 is much greater than Wp, N2 by N1 is nearly equal to Wp by, that is, this is much greater. So, we have neglected, then T43 cancels, and we have Wp by T21. Now, let us take equation 2, that is the second equation there. We had written 4 equations, and the second equation dN3 by dt is equal to this. So, let us look at this. From equation 2, which is written here, when you put that equal to 0, you can write this way and simplify it further, and we get an expression for N3 by N1. Now, we have an expression for N4 by N1, N3 by N1 and N2 by N1. Why did we want this? Because we wanted to use the equation that n, capital N, that is the total number, is equal to N1 into 1 plus N2 by N1 plus N3 by N1 plus N4 by N1. So, we have got all these terms now, so that we can relate the population inversion to the total number of atoms n. All right. So, from C and B, so C equation here and B in the previous here. So, equation B, we can write, if you subtract, one is N3 by N1, other is N2 by N1. So, N3 minus N2 by N1 comes out to be this, and which is equal to this. There are no approximations, only approximation we have made is T43 is much greater than Wp or delta n. So, N3 minus N2 now we call as delta n. In the 4 level, in the 3 level system, we called N2 minus N1 as delta n. In the 4 level system, we call this as delta n. So, this is, that is N3 minus N2 as delta n, because delta n here represents the extent of inversion the magnitude of inversion n3 minus n2 is delta n. So, n3 minus n2 by n1 is equal to, so this expression. So, we have got the expression here. Note that delta n, for delta n to be greater than 0, we need T21 to be greater than T32. All other numbers are positive, and therefore, delta n, that is greater than 0, or population inversion is possible if T21 is greater than T32. That is, the rate at which atoms go from here to here, if this is faster than the rate at which atoms come from here to here, there will be population inversion. Mathematically, now we see that yes, we have got the same expression. So, this is what we discussed qualitatively, that the requirement is T21 must be greater than T32. So, we have to look for a laser medium where the lifetimes or the transition rates are such that T21, that is from the lower excited states, the transition rate is much faster compared to the upper excited state, or if the upper excited state is a metastable state. Okay. So, that I have rewritten here, n3 minus n2 is equal to delta n into this. Therefore, for population inversion, we must have T21 greater than T32. Note that there is no condition on WP, the pumping rate. In a 3 level system, we had a condition on WP, that is the pumping rate. There was a pumping rate has to satisfy this condition. But now there is no, whatever be the pumping rate, so long as you have T21 greater than T32, you will be able to achieve population inversion. So, as before, we can use this expression. We have got A, B, C, n2 by n1, n3 by these expressions we have in terms of the rates, and WL is equal to I nu into sigma nu, the cross section by h nu. This is the definition of WL. Similarly, for WP, and IS is h nu divided by cross section into tau s, where tau s is this. So, with these expressions, we can show, as before in the 3 level case, I had shown that delta n can be written as delta n0, which depends only on the pumping rate WP, divided by 1 plus I nu by Is. We can write exactly similar expression here, only the expression becomes slightly lengthier because there are many more transition rates in the 4 level system, but you can get the same expression as delta n0 divided by 1 plus I nu by Is, and therefore, gamma of nu is equal to, we know that gamma of nu is equal to sigma of nu into delta n. The gain coefficient is given by this, and therefore, once delta n is in this form, then you will have gamma of nu is equal to gamma 0 of nu divided by 1 plus I nu by Is, which is called the saturated gain coefficient. So, we have got almost similar expressions, same procedure, but note that in a 3 level system, there was a condition on the minimum pumping rate which is required to achieve population inversion. So, we calculated that in the case of ruby laser, that threshold pumping rate is of the order of kilowatt. Here we do not have such condition. What the requirement is, T32 should be slower, or T21 should be faster than T32 for population inversion. All right. So, as before, it is written as before, the discussion is the same. WP, if WP increases, tau s decreases, we can see the expression, tau s is here. So, if WP increases, tau s decreases, this WP is negligible compared to the T21 here, and therefore, as WP so it is written here, as if WP increases, tau s decreases. and that implies IS saturation intensity increases and also gamma 0 of nu increases. So, just as in the case I discussed it earlier in this lecture, that for the 3 level system, for different pumping rates we had different gain curves, that is the small signal gain coefficient increases. So, this is for WP1. So, gamma 0 here, this value here, and this is gamma 02 small signal gain coefficient, which goes on dropping down as the intensity increases. The saturation intensity is shown here. This is the saturation intensity for the second case. So, the saturation intensity also increases. So, now we come to the summary of this 4 level laser amplifier. So, we have a 4 level system which comprises of 3 excited states and the ground states. This is the schematic that we show, but as I explained in the case of a 3 level system, the excited state, this itself may comprise of several states or maybe bands. We will see this may be several bands. We will see this in next, we will see the example of a Nd:YAG laser, where I will show that the 4th level, which I am indicating here as level 4, may comprise of 2 or 3 bands, and atoms are pumped to these bands. So, atoms may be raised to these bands, because if you take usually, if we will see in the next lecture, that Nd:YAG laser is pumped by krypton flash lamp. These days of course, diode pumped solid state lasers will also be discussed later, but if you use krypton flash lamp, it has several lines which will raise atoms to these bands, and these bands within themselves have very rapid transitions from here to here, and then from this level it comes down to the lower level, which is here. In other words, the level 4 itself may comprise of several levels, but we do not call this as a 5 level or a 6 level laser. This is still a 4 level laser, and the pump band, all of them are represented by level 4, from where atoms make rapid transition to a metastable state. This level 3 is a metastable state where the atoms have to accumulate. I am repeating this part in this summary, that atoms are excited to an upper state or states, from where they rapidly decay to a lower state, a lower excited state, and if that state happens to be a metastable state with a long lifetime, then atoms tend to accumulate at that level. The next excited state, if it has a fast transition to the ground state, then we can always achieve population inversion for any pumping rate between these 2 levels. This is the mechanism of achieving population inversion in a 4 level system, and a signal which corresponds to the energy difference between level 3 and level 2 will get amplified. Once population inversion is created, then this signal will get amplified by stimulated emission. So, the necessary condition for population inversion is T21, this transition must be faster compared to T32. We will take up in the next lecture the example of a Nd:YAG laser amplifier, which is widely used and which is a very nice amplifier to discuss. The picture will become more clear. Thank you.